Hello, it's Keith here, and this is lesson 10 in the YQuest series. We're porting YQuest to a bunch of different systems. This time it's going to be the Super Nintendo. Now, we looked at the NES last time and there was a bit of a pain because we have to deal with vblank and we have to write all of our data during vblank. The same is the case on the SNES, but the SNES is a bit easier because we have a lot more memory, so we don't have to be a bit tricky with the buffer, and the CPU is so fast, and it has a DMA that can directly transfer all the data for us, so it's not going to be anything like as difficult. Well, let's just have a quick look at YQuest. Let's see it in action, just so I can prove it does actually work. So you can see here's the game. It's got sound thanks to the SPC 700 driver chibi sound that I wrote before. Only very simple sound, but it's sound all the same, which somehow feels like an achievement. You can see the movement's a bit jerky because we're only using the tilemap. We will be porting a hardware sprite version of this game later on, but at the moment we're simply using the tilemap. Now, this game example was based on this simple series that I did before, and that also only used the tilemap, so that's kind of the reason why the graphics were a little bit limited. But as I say, it's just a simple example that hopefully you can build on for your own little games. Let's go over to the source code and let's check things out. Okay, so here's the source code. If I just get back to the top of it. Very good planning there. Okay, so here's the start of the code, and we're going to go through all of it and discuss how it works. Now, the first thing you'll see here is there's some collision masks. Now, because we're using the tilemap, the internal calculated resolution and the displayed resolution don't really match. So to make sure that the collision is occurring at the same resolution that it's been shown and that the player doesn't think they're safe but they're actually partially overlapping, we're reducing the resolution of the collision detection here to match the visual representation. We're then defining the screen size here, and this is so that the multi-platform code is working correctly for this screen size. We're then defining some registers, some zero-page entries that I use to simulate Z80 registers, user RAM, which is the game's variables, and also the SNES screen buffer. Now, this is a copy of the tilemap, and it's going to be transferred during vblank, so we'll see that later on. Our code starts at hexadecimal 8000. We're turning on our screen here. This is basically stuff we've all seen before, I think. We're defining our palette here, and we're setting the scroll position. So this is just setting up a starting screen. Now, first here, we're clearing the buffer that is going to be used for the tilemap, and then we're defining the tile pattern data here, transferring it into VRAM, and then here we're turning on the screen. So we've got the screen on here. Finally, we're running this chibi sound init. Now, this transfers the driver code that I wrote from the ROM cartridge to the SPC 700 and starts it up, because if you don't know, making sound on the Super Nintendo is a little bit tricky. You have to have some code for this weird processor, the SPC 700, and so hopefully my chibi sound code can at least make a few simple beeps for us. At least it seems to here. And then finally here, we're turning on interrupts. We're doing that because we need this vblank interrupt to work, otherwise we'll get no graphics on the screen. So that's quite important. Next, what we're doing here is we're clearing the game data. The user RAM is the game variables. You can see we defined it up here. And we're now just clearing that out using this cldir command, which is in my common code. And then we are starting a new game. So we're setting up the lives, the level, we're silencing the sound, clearing the screen, and then we're showing the title picture to the screen, which is a fine thing you can see up there. What we're doing here, we've got 1 byte per tile. We're loading in each one, checking if it's non-zero, and using the show sprite routine, which does most of the graphics really. The font's a slightly tweaked version, but basically the font, the tiles, it's all the same stuff. So that does the work there. We just repeat until we've shown all the tiles to the screen. Here we're just showing some text to the screen. You can see all up there, press fire, learn ASM.NET, wonderful things like that. And here is the start of the new level code, which runs for the first level and every subsequent level. We wait for the fire button to be pressed, clear the screen, center the player, and then we define the objects that are on that level. Nice and simple. Here, the X register is being used to store any directions that are pressed. The Y register and the B zero-page entry are being used as a delay. So make these smaller if you want the game to be faster, make them higher if you want it to be slower. Super Nintendo is very fast. I've had to use a pair of registers here. So we read in from the joystick and we see if any buttons are pressed, and if they are, we store them in X. Okay. So here's the part of the drawing routine that starts first. We're drawing the user interface, that's the text in the corners of the screen. We're then blanking the player sprite. Now, IX is a zero-page pair, and that points to an object, and that object has a sprite in an X and Y position, acceleration, so on. And so the player object is the player's Y, basically. And so we're just clearing that off the screen there. Now, we have this thing called key timeout. The game works by acceleration, so if I hold the up button, I'll keep getting faster. But if I just process it every tick, it'll get too fast too quickly. So we have a timeout, and while that timeout's greater than 0, we ignore any holding of the keys. So that's what that does here. And these are the key processing. We're checking each direction, and we're altering the acceleration of the player with y acceleration and x acceleration here, and these are offsets to the player object in IX here. So we're using this dec IX offset by y and inc IX offset by y, and these will actually change the acceleration within the player object here. Now here's the fire button routine. This is the fire routine, which is in the common code, and here is the fire 2, which will stop acceleration, so it's like an immediate brake, which is very handy for these two fire button systems. We then store the new timeout if it's been changed. You can see we'll be setting it here for the up, down, left and right. And then we do all of the game logic, draw the sprites to the screen, handle any collisions and game overs, wonderful things like that. Here's the loop. We loop all the way back here to the start of the main loop here. Just keep going forever. Our clear screen routine is very basic. We're just using show sprite to set each of the tiles to tile 0, which is the space. Print char is our character drawing. Now the tiles are defined that the first 96 are our font and the remaining ones are our game sprites, so all of that kind of weird stuff up there you can see. So when we are doing a character, we subtract 32 because there's no characters below 32 in our font. We calculate the x and y position from the cursor here. We run show sprite and then we increase the x position here. Now blank sprite will use the object in IX and it will clear that object off the screen. So this is used for removing the player and things like that. Now a collision of 254 is a dead object, 255 is an uninitialized object, so we don't want to draw those. Anything else we do want to clear, and what we're doing is we're using the space within the tile and we store that in ZH here. Get sprite address calculates the tile number we want to show to the screen. So if we want to show sprite 1, we need to calculate firstly that is offset to pattern 96 plus because the first 96 are the font, and then we also need to calculate the sprite frame because there's 4 banks of animation for the sprites. So we multiply the sprite frame by 16 because there's a total of 16 sprites per bank, and we store that up, and that is the final pattern number that we want to show to the screen. Do get sprite object will get all of the data from the IX pointed to object. So we calculate the sprite for here from that offset in there, and we calculate the x and y position. We're multiplying them up here. We're just converting those for a tile position. There is planned that there's going to be a version of this game that uses sprites later on, so the fact that we've got a bit of extra resolution will come in handy then. So we'll see that later on. Here's the show sprite routine. We use get VDP screen pos, which actually calculates a position in the buffer. We then write the 2 bytes that define that tile's definition into the buffer. Now in the simple series we were writing straight to VRAM, but that's not going to be appropriate for a game with potentially too much animation here. Maybe we'd get away with it, maybe we wouldn't. With Grime 6502 we didn't, there were glitches, so we used the buffer there, and I thought it would be nice to have this simple series give a good example of some solid code you could build on, so we're using that buffer again in this case. Okay, here's get VDP screen pos. Now basically it's almost the same as before. We're calculating the memory offset of the tile in the same way as we did in the simple series. The only difference is now, rather than writing those to the VRAM and port select, we're just adding the buffer and using those as a memory address we want to write to. Unlike the NES version, the SNES version is just the entire tile map as is. The NES, because of the limited speed, we had to actually store the byte locations we wanted to change and the new byte for those locations. The SNES one, we're transferring the entire tile map in one go during vblank. Define tiles transfers our pattern data into VRAM here. You can see here we're writing them in 2 bytes here. We write to 2119 first and then 2118. That will come up later. Prepare VRAM selects the destination address. We have to wait for vblank, and then we select the VRAM address. This is used by the define tiles. It's not used by the setting tiles routines, of course. Wait vblank. We'll check this top bit here of 4212 and wait for us to be in vblank. Okay. Now here's the tricky bit. We've got this non-maskable interrupt handler, and this is going to be running during vblank, and this is going to transfer all of the data in one go from RAM to the tile map, and it does it with a DMA. Okay, so how do we use this? Well, first we need to select the destination address. We're doing that here. Then we need to change the address that increments. Now usually we are incrementing on the right to 2118 here, but that's not what we need in this case. We need to increment on 2119. So we're setting that here. We're then setting to write 2 bytes in one go. Here we're selecting the 1 byte destination address. It's got to go somewhere starting in 21, but we want to go to 2118. and that's why we've set the auto ink to occur on 2119 here. We then select the source address, which is our SNES screen buffer. Now this is a 24-bit command, so even though we're only running in 8-bit mode, if we were running in 16-bit mode, we would want a larger address, but we're only going to need to use 2 bytes of this, so the third byte is unused here. And then we are specifying the number of bytes to transfer, and again we're only needing to transfer a relatively small number. Our tile map is 32 by 32 and there's 2 bytes per tile, so we're just multiplying that up there. We're disabling something called HDMA transfer. Now I'll be honest, I don't really know what that is, I just know we don't need it, so let's turn it off. And then we start the transfer with this command here. Now once that happens, effectively our code will halt for a brief moment, the transfer will occur, and then everything will carry on. So it's very, very fast. So we don't need to worry about that. It's just it effectively has happened, and that's all we need to do. So there's a lot of commands here, but it's a lot better than some nasty great loop transferring the data slowly. So that's what we've done. What we do need to finish off is changing the write to auto increment back on 2118 rather than 2119, because our other code is relying on that. We're writing to 2119 then 2118. So we just need to make sure everything's back the way it was before we started. Here's our read controls routine. This is actually the same as the NES one. This is some of the backwards compatibility from the old NES days. The SNES was originally going to be backwards compatible, you see. That's why they chose the 65816 rather than the 68000, I think. So we have some NES compatibility. Anyway, we strobe the joystick ports, and then we read in 1 bit at a time from 4016 here, and this will give us the main directions here in order, which is what we want. So we're reading those in. Our wait for fire routine will use those, and it will wait for fire to be pressed down and then released, and it re-randomizes the random number generator while it does that, just for some randomness. So that's what we use when we need to stop the action for a moment, like press you've died, you know, game over, or you've completed a level, well done, things like that. That's in the wrong place, that should be a bit further up. I'll put that up there. Okay. Here's the common code. Obviously there's far more code than I'm showing you today, quite a lot more code, but it's all common to all of the other systems. So I've not done specific episodes on that. Please see the Z80 ones, the code is almost identical. I made all the labels are the same, the functions are the same, so I did about 5 lessons on that. I didn't want to do another 5 saying the exact same thing again because I thought it'd be quite boring, so I didn't. Here's the font and the 4 banks of sprites. Now, unlike with the Grime series, the font, as you can see, is full color, so it's in native format, so rather than 1 bit per pixel being converted up. Here's our palette. Also, unlike the Grime series, it's in native format. One of the other things I've been doing is I've been modifying YQuest Sprite Editor, giving each system a native palette export option. So if you prefer that rather than my common code, there you go, you've got it. Here's the footer. There's some common stuff here just to define a valid cartridge. And here are the vectors. Now, we're in 6502 mode, but we need to define a 68000 one as well. So we have. Now, this is the start of our code. Actually, I think that was probably a bug. That probably should be filled in. Anyway, so we're starting at hexadecimal 8000, which is the start of our cartridge. And our NMI handler is the vblank handler, a non-maskable interrupt. There it is. So that's the important thing for our vblank interrupts. And there we go. That's all the code. So as I always say, you're welcome to go to my website and download this and modify it and make your own games from it and hopefully sell them for tons of money, and you don't need to give me credit. I'm not sure anything that's going to happen, but we can hope, and you're certainly welcome to try. Anyway, as I say, please go ahead and download it and do whatever you want and try and learn from it. I hope it's useful to you. But whatever you decide to do, I hope you've enjoyed this. If you have, please like and subscribe. It helps Google with the analytics. They recommend the videos based on likes, and subscribing gives me encouragement to keep working like a crazy fool on these things. So if you want to see me make more stuff, then please do that. Anyway, take care of yourselves. Good luck with your programming. Thanks for watching, and goodbye.